Welcome back to Mr. Vaughn's classroom. Before we get started, please take a moment to hit the subscribe button and give this video a thumbs up. Today, we're looking at Unit 5, Introduction to Exponential Functions, and we are on Lesson 6, Analyzing Graphs. Our learning goal today is to compare situations where quantities change exponentially. We have two learning targets today. As we work through the practice problems, keep these two learning targets in the back of your mind. Notice how they relate to the practice problems we do, and try to make sure you are comfortable making these two statements by the end of the lesson. Learning target number 1, I can use graphs to compare and contrast situations that involve exponential decay. So what they're really looking for is, are you able to look at a graph where you have more than one situation on the graph and be able to tell which one is decaying at a more rapid rate and which one is decaying at a slower rate. Learning target number 2. I can use information from a graph to write an equation that represents exponential decay. If you remember from a previous lesson, you can use a graph to write the equation. The first thing you need to know is the vertical intercept, because that will be your starting amount. Then you need to know 2 points, and you need to know the y values of those points. If you take the second y value and divide it by the first y value, that will give you the growth factor. With those two pieces of information, you can then write your exponential function so that it is y equals your initial amount times your growth factor to the power of x. And we have one glossary term for this lesson, and that is growth factor. In an exponential function, the output is multiplied by the same factor every time the input increases by 1. The multiplier is called the growth factor. Now we can begin the practice problems. Our first practice problem says, the two graphs show models characterized by exponential decay, representing the area covered by two different algae blooms. In square yards, W weeks after different chemicals were applied. So as we look, number 1 asks us, which algae bloom covered a larger area when the chemicals were applied? Explain how you know. So if we want to know the area when applied, this is going to be the vertical intercepts. For the red triangle, we see that right here at 500 square yards. For the blue circle, we see that down here at 200 yards. So for number 1, red triangle algae bloom covered a larger area because its vertical intercept is larger. And I'll go ahead and put 500 square yards is greater than 200 square yards. Now we can look at number 2. Which algae population is decreasing more rapidly? Explain how you know. So what I want you to look at is this point right here where it's been 5 weeks since the chemicals were added. At this point, both of the symbols are one right on top of the other. So they're both at a population just above 60 square yards maybe. But we know that the red triangle algae had to go all the way from 500 down to about 60. While in that exact same 5 weeks, the blue circle algae only had to go from 200 down to about 60. So notice the line for the red triangle algae is much steeper than the blue circle algae. So that means the red triangle algae bloom is decreasing more rapidly because the initial amount was much higher, but both reached the same amount after 5 weeks. The steeper slope means a higher rate of change. If you have any questions about how to solve this practice problem, please leave a comment below and I'll get back to you with any assistance I can offer you. Our next practice problem says a medicine is applied to a burn on a patient's arm. The area of the burn in square centimeters decreases exponentially and is shown in the graph. Number 1 asks us, what fraction of the burn area remains each week? So now they're telling us that this graph is decreasing exponentially. So what we need to do is find 2 points where we know what the values are. And I'm going to take the initial point right here, and I can see that that is at x is 0, y is 8. Then I see the next point is right on a crosshair. And that happens when x is 1 and y is 6. So now that I know 2 points, what I can do is take the second x value, which is 6, and divide it by the first y value, which is 8. And I can simplify this by dividing the top and the bottom by 2. 6 divided by 2 equals 3, and 8 divided by 2 equals 4. So 3/4 of the burn area remains each week. Number 2. Write an equation representing the area of the burn A after T weeks. So, we're going to say that this expression is A, and A is going to equal the initial amount, which comes from my vertical intercept, and that tells me my initial amount was 8. I'm going to multiply that initial amount by the growth factor, which we just said in number 1 is 3/4. And my exponent is going to be the input, and they told us to use t for the time in weeks. So the equation that represents this situation is A equals 8 times 3/4 to the power of t. And number 3, what is the area of the burn after 7 weeks? Round to 3 decimal places. So if you notice, they've asked you for 7 weeks, and that is not on the graph. So they want you to use the equation we just found in number 2. So A equals 8 times 3/4 to the power of 7. So you bring up a calculator and you put in 3/4, which is equal to 0.75. Now, you want to take that to the exponent of 7. And that gives us 0.13, and so on. We're going to multiply that by the original amount, which was 8, and we get 1.068 because they want us to round it to 3 decimal places. And this 8 tells us to round the 7 up to 8. So our final answer is 1.068. And that is in square centimeters. If you have any questions about how to answer this practice problem, please put a comment below and I'll give you any assistance I can offer. Our next practice problem says the area of a sheet of paper is 100 square inches. Write an equation that gives the area A of the sheet of paper in square inches after being folded in half n times. So, for number 1, the first thing I need is the name of the function. And here they tell us to use capital A. The next thing we need is the initial amount. And right here they tell us it's 100 square inches. So A equals 100. Now we need to know what the growth factor is that we're going to multiply by. And here it tells us it's being folded in half. So if a paper is folded in half, it has 1/2 of its area remaining each time it's folded. So we're going to multiply by 1/2. And the last thing we need is the input, and they're telling us right here to use n for the number of times the paper is folded. So this is how we create the equation for number 1. Next, we have number 2. The area of another sheet of paper is 200 square inches. Write an equation that gives the area B of this sheet of paper in square inches after being folded into thirds n times. So again, the first thing we need is the name of the function. And they tell us right here we're going to call it capital B. Then we need the starting amount. And on number 2, they tell us the starting amount is 200. Now we need to know what the growth factor is. In number 2, the paper is being folded into thirds, which means after each fold, there is 1/3 of the area remaining. So we're going to multiply by 1/3. And the last thing we need is the exponent, and they tell us right here we're going to use n as the exponent. Number 3. Are the areas of the 2 sheets of paper ever the same after each being folded n times? Explain how you know. So for number 3, what I'm going to do is create a table. We're going to have a column that is n, the number of times the paper is folded. We're going to have a column for paper A, and we're going to have a column for paper B. Now, initially, the papers are not folded at all. And paper A is 100 square inches, and paper B is 200 square inches. So paper B is larger at this time. Now, each paper will get folded once. Paper A is multiplied by 1/2, so 100 times 1/2 becomes 50. Paper B is multiplied by 1/3. So 200 times 1/3 gives us 66.7. We can see that after one fold, paper B is still larger. They're still not the same size. So now we can fold a second time. Paper A again is multiplied by 1/2. So 50 times 1/2 is 25. Paper B again is multiplied by 1/3. So when we multiply by 1/3, our paper is now 22.2 square inches. And notice paper A is now the larger paper. So these two papers have now changed which one of them is larger. And after this point, paper B will continue to get even smaller than paper A. Never the same size. If you have any questions about how to solve this practice problem, please drop a comment below and I'll get back to you with any help I can offer. Our last practice problem says the graphs show the amount of medicine in 2 patients after receiving injections. The circles show the medicine in patient A, and the triangles show that in patient B. One equation that gives the amount of medicine in milligrams M in patient A, H hours after an injection, is M equals 300 times 1/2 to the power of H. What could be an equation for the amount of medicine in patient B? So, the first thing I would need is to figure out the numbering on these axes. Notice that on the equation for patient A, we know that circles represent patient A. And we can see that the number by itself is 300. So that means the initial amount was 300. So if I look at the vertical intercept right here, this point must be 0, 300. So if I were numbering this, then this line is 300, this line is probably 200, and this line is probably 100. And then if I am labeling the hours, these hours are probably increasing by 1. So, my first piece of information is that if this is 0, 300, then we can assume that the other vertical intercept, the triangles, are patient B, then this must be 0, 200. So we can get rid of A and we can get rid of B because those two both say the initial amount is 500, but if A was only 300 and B is below 300, then it's impossible that A or B are correct here. So now what we need to know is, are we multiplying by 3/10 each time, or are we multiplying by 7/10 each time? So let's test that out. 200 times 3/10, which is equal to 0.3, would equal 60. So this should have a point at 160. If D is correct, then 200 times 7/10, which is equal to 0.7, the next point would be at 1/140. So let's see which one makes sense. If this line here is 100, and the next triangle is above 100, then this red triangle must be at 1/140, because 160 would be down here somewhere below it. So that means C cannot be correct. D must be the correct answer. If you had any questions about any of these practice problems, please leave a comment below and I'll get back to you with any help I can offer. Now, before we finish this up, let's go back and look at our learning targets and make sure you understand everything from this lesson that you should. As we look at our learning targets, number 1 says I can use graphs to compare and contrast situations that involve exponential decay. As you are comparing graphs, remember, the steeper the change of rate is, the faster it is. The flatter that change of rate is, the slower it is. Learning target number 2, I can use information from a graph to write an equation that represents exponential decay. Remember, the first thing you need is the initial amount, and the initial amount is found in the y value of the vertical intercept. Then you're going to multiply that by the growth factor, and you can find the growth factor by taking the second y value and dividing it by the first y value. And then you will raise or multiply that growth factor by the exponent of the input, or the x value. If you understand these two learning targets, then you've learned what you were supposed to in this lesson, and you're on a good path. If you still have questions about either of these two learning targets, please drop a comment below, and I'll get back to you with any help that I can offer. Thank you again for taking the time to watch this video. If you found it helpful, please hit the subscribe button and give this video a thumbs up, and I invite you to please leave a comment below. I look forward to seeing you in the next lesson.